if you look back at traditional cybersecurity, I mean, the whole industry was basically built on this expectation of rigid predictability.
Oh, absolutely.
It was essentially medieval fortress building, right? You construct the stone wall, you write a static firewall rule, and when a packet of data hits the perimeter, the system checks it against a list.
Yeah, a very literal list.
Right, and if the signature doesn't match, it gets blocked. It's entirely binary.
Right. It is completely deterministic. You write the rule, if X happens, execute Y. But the problem is modern threat actors, they don't really play by deterministic rules anymore.
No, they definitely don't.
When you are dealing with, say, polymorphic malware that mathematically alters its own signature every single time it replicates, a static rulebook is just virtually useless. I mean, a single changed bit renders your entire firewall rule obsolete.
Which brings us to the core of today's deep dive. If you're gearing up for the CompTIA SecAI Plus exam, or honestly just trying to defend a modern network, Domain 1 is an absolute beast.
It is a massive amount of material.
It really is. So today, we are cutting through all the textbook fluff.
Yeah.
We're synthesizing the official CompTIA study guides, the MITRE ATLAS frameworks, and those really great Private 16 lecture series to just unpack how AI is fundamentally rewriting the rules of network defense.
And to do that, we have to move from deterministic thinking to probabilistic thinking.
Right.
We are no longer writing rigid rules. We are training algorithms to evaluate patterns, assign confidence scores, and, identify threats they have never explicitly seen before.
Let's unpack that shift, actually.
Mm-hmm.
I always look at traditional computing like a bouncer at a club, checking IDs against fixed VIP list.
Okay, yeah.
If a brand new threat shows up like a zero-day exploit that just isn't on the signature list, the bouncer just lets them walk right through the front door. Machine learning, on the other hand, is like putting a highly trained detective at the door.
Exactly.
Yeah.
Because the detective doesn't need a list. They are looking at behavioral anomalies.
Right.
Like, is the person sweating? Is their walking cadence slightly off? In network terms, machine learning doesn't really care about the file hash. It cares about the behavior. And the only way to build that detective is by feeding it massive amounts of data.
And the frameworks highlight different architectures for actually doing that. There is deep learning, which uses artificial neural networks with all those hidden layers to autonomously discover patterns without a human, like manually tagging the features.
Right.
Then there are transformers, which rely on attention mechanisms to understand the context of sequences, which is, why they absolutely dominate natural language processing right now.
Yeah, they are everywhere. But the architecture that really turns the tables in cybersecurity, that's generative AI.
See, this is what I have to push back a little. We usually think of Gen AI as large language models writing emails or generating images. How does a generation engine actually help a defender?
Well, it's through generative adversarial networks, or GANs. You basically pit two neural networks against each other. You have a generator and a discriminator. The generator creates synthetic data, and the discriminator tries to tell if it's real or fake.
But wait. Training two neural networks to constantly fight each other via backpropagation?
Yeah.
That sounds like an absolute nightmare for compute costs and memory bandwidth. Like, who actually has the budget to run that continuously?
Well, you're not wrong. It is incredibly resource intensive, which is why it's usually done in specialized lab environments rather than out on the edge.
Makes sense.
But the return on investment is massive. Defenders use the generator to synthesize fake, highly realistic malware variants. You are basically using AI as a sparring partner.
Fighting fire with synthetic fire.
Exactly. You use it to train your defensive models against attacks that haven't even been invented in the wild yet.
I really like that. But to build any of these models, obviously you have to train them. The SecAI Plus syllabus zeroes in on 3 primary machine learning methods that you just have to know: supervised, unsupervised, and reinforcement learning.
Right.
Let's start with supervised learning. This relies entirely on labeled data, where you explicitly tell the system, this file is spam, this file is safe.
Yeah, the algorithm is mathematically drawing a boundary line, they call it a hyperplane, between the safe data and the malicious data. It's highly effective for malware classification, but it does introduce a critical vulnerability, which is label poisoning.
So if an attacker can gain access to your training dataset and slightly alter the labels, they aren't just breaking the model, they are fundamentally shifting that mathematical boundary.
They shift the hyperplane just enough so that their specific family of malware suddenly falls onto the safe side of the line. The model operates perfectly. I mean, it was just taught the wrong definition of reality.
That is terrifying. Which brings us to unsupervised learning. Attackers rarely label their zero-day exploits for us, so we have to use raw, unlabeled data.
Right. The algorithms have to find the hidden structures on their own, and the exam heavily emphasizes k-means clustering for this.
Let's break that down, actually. We throw around k-means clustering a lot, but what does the k actually stand for?
The k just represents the number of center points, or centroids, that you want the algorithm to find. It
Right.
plots all the raw network data in this massive multidimensional mathematical space. Then it measures the distance between data points, behaviors that are mathematically similar, physically grouped together around those centroids.
So it establishes a baseline of normal without any human guidance at all.
Right.
So this is the engine behind user and entity behavior analytics, or UEBA. When a zero-day exploit hits, the AI doesn't recognize the attack signature. It just sees a data point that is mathematically orbiting way outside the normal cluster and flags it.
Precisely. It catches the unknown unknowns.
But doesn't that just create a massive headache for the SOC team?
Mhm.
I mean, if UEBA flags anything outside that cluster, every time an admin runs a novel, totally legitimate PowerShell script, the alarms go off.
Oh, yeah.
The false positive rate must be completely unmanageable. Furthermore, what if an attacker is slow? Like, what if they subtly alter their behavior over 6 months to slowly drag the centroid toward their malicious activity?
Well, you've just described the boiled frog attack, which is the primary vulnerability of unsupervised learning.
Yeah.
You are essentially trading zero-day detection capabilities for alert fatigue and baseline drift.
Gotcha.
This is exactly why you cannot rely on unsupervised learning alone. You often have to layer it with reinforcement learning.
And reinforcement learning, or RL, operates completely differently.
Right.
An autonomous agent learns through continuous trial and error using a mathematical reward and penalty loop.
The Microsoft Cyber Battle Sim is the gold standard example here. You place an AI agent in a simulated network environment.
Right.
The state is the exact condition of the network at any given millisecond. The agent has to take an action, and the environment gives it feedback.
So if the AI agent dynamically tunes a firewall to block an incoming DDoS attack, it gets a positive reward, like a +1.
But if it panics and blocks the primary revenue-generating server, dropping legitimate customer traffic, it receives a massive negative penalty.
Ouch.
Yeah, so over millions of iterations, it learns the optimal policy for defending the network just by interacting with the consequences of its own actions.
Okay, so we've got our training methods down, but there is a massive elephant in the room here: data privacy. Training these models requires terabytes of data.
It does.
What if that data is protected patient health information under HIPAA or European consumer data under GDPR? You can't just dump all those private records into a centralized cloud server.
No, doing so would trigger massive compliance violations. And this is why decentralized architectures like federated learning were developed.
I always explain federated learning with a franchise restaurant analogy. Imagine each local hospital is a franchise kitchen.
Okay.
They want to help corporate create a master recipe, but they absolutely refuse to share their secret ingredients, the patient data. So corporate copies the master recipe and sends it down to the local kitchens.
Right. And the model trains locally on the private data at that specific hospital. The raw data never moves across the network.
The local kitchens just test the recipe and send back the final feedback. But what actually travels over the wire?
Just cryptographic mathematical updates, specifically the weights and gradients. They essentially tell the central server, hey, increase the weight of this variable, decrease the weight of that one.
Oh, okay.
Yeah, the global model updates based on those mathematical tweaks without ever seeing the raw data that caused them.
But MITRE ATLAS still flags this as a high-risk architecture. If all I'm sending is a recipe tweak, how is that a vulnerability?
Because of model inversion attacks.
Ah.
If an attacker compromises the central server or intercepts the transmission of those updates, they can reverse engineer the weights.
Yeah.
By observing exactly how the model adjusted, a sophisticated attacker can mathematically reconstruct the sensitive data that caused the adjustment.
That is wild.
And furthermore, a malicious edge client could send poisoned weights, infecting the global model.
So, whether trained centrally or federated, you cannot deploy a model without rigorously proving it works safely. Quality control is paramount, which means model validation and fine-tuning.
Absolutely. You must test the model against unseen holdout datasets to ensure it actually learned the underlying logic, rather than just memorizing the training data.
Right.
And to measure that success, we use specific metrics: precision, recall, and the F1 score.
The SecAI Plus exam loves the F1 score. It defines it as the harmonic mean of precision and recall. But why a harmonic mean? Why not just take a standard average of the two numbers?
Because an arithmetic average hides terrible flaws when dealing with extreme class imbalances. In cybersecurity, you might see 10 million benign packets and only 10 malicious ones.
Right, it's a needle in a haystack.
Exactly. So if your model just lazily labels everything as benign, your precision looks amazing, but your recall for catching actual threats is literally zero. A harmonic mean aggressively penalizes extreme imbalances.
I see.
It forces the model to prove it is highly capable of both catching threats and avoiding false alarms.
Validation also mandates adversarial testing, actively trying to fool the model and bias auditing. Like, if a model was trained on historical HR data to flag insider threats, you have to audit it to ensure it isn't skewing its predictions based on protected demographic attributes.
Spot on. And once validated, you move to model fine-tuning. The syllabus highlights 3 critical adjustments: epochs, pruning, and quantization.
Okay, an epoch is one full pass of the training dataset through the algorithm.
Yes.
But you have to thread the needle. Run too many epochs, the model overfits and memorizes the data. Run too few, it underfits and learns nothing.
Right. Then you apply pruning. You mathematically delete the neural weights that are close to zero. You are basically cutting the weak connections that don't heavily influence the outcome, which drastically reduces the memory footprint of the model.
Which perfectly sets up quantization.
Yeah.
I think of this like taking a massive uncompressed 4K image and saving it as a 1080p JPEG. You lose a microscopic amount of detail, but the file loads 10 times faster.
That's a great way to put it. You are mapping high-precision data types, like 32-bit floating point numbers, down to lower precision integers. In network defense, where you are analyzing millions of packets a second, that optimization is the difference between catching an attack or lagging behind it.
But even an optimized model isn't set and forget, right? The moment you deploy an AI, you are freezing its understanding of the world. But threat actors evolve.
Yeah.
If you don't schedule regular model maintenance and retraining, the model's predictive power just degrades.
Yeah, that degradation is called concept drift. It's exactly why you must enforce a human-in-the-loop design using confidence level monitoring. If the AI is only, say, 60% sure about a classification, it should automatically route that prediction to a human analyst. The system must acknowledge its own limits.
We've covered the underlying mechanics of every major training technique. But before we wrap this deep dive, I want to leave you with a final thought to mull over. We've talked extensively about how defenders use AI, but threat actors are using the exact same architectures to automate attacks at machine speed. When AI inevitably fights AI on the network edge, does the ultimate advantage go to the side with the better data or the side with fewer ethical guardrails?
Oof. That will be the defining cybersecurity question of the next decade.
It really will.
Yeah.
Now, as promised, to ensure you are totally locked in for the SecAI Plus exam, we are putting everything we just discussed to the test.
Let's do it.
We are running the ultimate audio flashcard gauntlet, covering all 9 major sections of Domain 1. 3 rapid-fire questions and 1 scenario-based PDQ per section. Let's hit it. Section 1, Types of AI. Question 1. What architecture is currently dominant for natural language processing and sequence analysis?
That would be transformers.
Perfect. Question 2. Which type of AI uses artificial neural networks with hidden layers to autonomously discover patterns in raw data?
Deep learning.
Question 3. What is a key security risk associated with AI-driven threat actors using automated data correlation?
Correlating millions of leaked credentials to generate custom targeted dictionary attacks instantly.
Yep. And your types of AI PBQ. A security analyst feeds a complex visual cloud network diagram into an AI to identify structural vulnerabilities. What specific type of AI facilitates this?
Multimodal AI, or a multimodal LLM, capable of processing diverse input types.
Nailed it. Moving to Section 2, Machine Learning. Question 1. How does machine learning fundamentally differ from traditional computing security?
Traditional computing is deterministic and rule-based. Machine learning is probabilistic and data-driven.
Question 2. What metric represents the harmonic mean of a machine learning model's precision and recall?
The F1 score.
Question 3. What phenomenon occurs when a model's predictive power degrades over time because real-world data behavior has changed?
Concept drift.
And your machine learning PBQ. You were tasked with analyzing terabytes of incoming network packets to find a zero-day exploit with no known signature. Which ML approach do you deploy?
Unsupervised learning to establish a baseline and flag deviations.
Excellent. Section 3, Generative AI. Question 1. What dual-use nature of generative AI is considered a central challenge in security?
Attackers use it to automate malware creation, while defenders use it for threat intelligence.
Question 2. What architecture uses a generator and a discriminator fighting each other to synthesize highly realistic data?
Generative adversarial networks, or GANs.
Question 3. How can defenders utilize generative AI to improve their own detection models?
By generating synthetic malware variants to train defensive systems against unseen threats.
Generative AI PPQ. An attacker uses an LLM to automatically map your organization's public profiles and draft personalized spear phishing emails. Which specific attack stage is the AI accelerating?
Reconnaissance, or OSINT collection.
Awesome. Section 4, supervised learning. Question 1. What is the defining characteristic of the data used in supervised learning?
It relies entirely on labeled data with explicit right and wrong answers.
Question 2. What are the most common cybersecurity applications for this method?
Spam detection and malware classification.
Question 3. What attack vector targets the training phase by manipulating input files?
Data poisoning or label poisoning.
Right. Supervised learning PBQ. Your malware classifier suddenly lets a specific family of Trojans through the network. Investigation shows the training dataset was altered months ago. What attack succeeded?
A data poisoning attack targeting the supervised learning model's boundaries.
Spot on. Section 5. Unsupervised learning. Question 1. What kind of data does unsupervised learning utilize?
Raw, unlabeled data.
Question 2. What algorithm is commonly used to find hidden structures and group similar data points?
K means clustering.
Question 3. What is a primary cybersecurity application for this learning method?
User and Entity Behavior Analytics, or UEB.
Unsupervised learning PDQ. A user logs in with valid credentials but begins aggregating files at 3:00 a.m. Traditional tools ignore it, but your AI flags it immediately. What baseline process enabled this?
Unsupervised anomaly detection identifying a deviation from the established behavioral cluster.
Great. Section 6. Reinforcement learning. Question 1. How does an agent learn in this environment?
Through continuous trial and error using a mathematical reward and penalty loop.
Question 2. What represents the state in a cybersecurity simulation?
The current condition of the network environment at any given millisecond.
Question 3. Which Microsoft framework is cited as an example of using RL for network defense?
The Cyber Battle Sim.
Reinforcement learning PBQ. An autonomous agent reconfigures firewall rules during a DDoS attack. It receives a +1 score for blocking malicious IPs and a -100 for blocking the revenue server. What training technique is this?
Reinforcement learning.
Exactly. Section 7, federated learning. Question 1. What is the primary benefit of this architecture?
It allows decentralized model training, keeping raw data on the edge to aid in IPR and GDPR compliance.
Question 2. What exactly is sent from the edge device back to the central server?
Cryptographic mathematical updates, specifically the weights and gradients.
Question 3. What major security risks are introduced by this architecture?
Model inversion attacks during transmission and poisoning from malicious edge clients.
Federated learning PBQ. 3 competing banks want to collaboratively train a fraud detection AI without exposing their proprietary ledgers to one another. Which architectural design should they implement?
Federated learning.
Home stretch. Section 8. Model validation. Question 1. What is the purpose of testing a model against unseen holdout datasets?
To ensure the model actually developed the logic to generalize rather than just memorizing the training data.
Question 2. What continuous validation practice routes uncertain AI predictions to a human analyst?
Confidence level monitoring, executing a human-in-the-loop design.
Question 3. Before deployment, what 2 specific audits must be performed during evaluation?
Adversarial testing and bias auditing.
Model validation PBQ. After fine-tuning, you discover the model heavily skews its predictions based on a protected demographic attribute found in historical data. What validation steps successfully caught this issue?
Bias and fairness auditing.
Finally, Section 9. Model fine-tuning. Question 1. What term describes the scheduled iteration and retraining of a model to counteract predictive degradation?
Model maintenance.
Question 2. Which technique involves reducing the size and complexity of a neural network by dropping zero-value weights?
Pruning.
Question 3. What fine-tuning technique maps higher precision data types to lower precision ones to optimize performance?
Quantization.
And your final PBQ. A hospital discovers their AI chatbot is providing answers based on last year's outdated medical policies. To align the model with the current year's reality without building from scratch, what overarching process must they initiate?
Scheduled model maintenance and retraining to combat concept drift.
That is the gauntlet. If you follow the mechanics behind those answers, you are in prime shape to dominate Domain 1. The digital perimeter is no longer a static wall. It's a living, probabilistic environment. Keep studying, keep adapting, and we'll catch you on the next deep dive.